Okay, good to have you here. We want to look at a chemical engineering software, UNISIM. So we want to use it and solve a reactor problem. So you are welcome to my channel. Now let's look at a problem that we would solve. Now this problem is gotten from a work done by Hamid of the Process Control and Safety Group, Department of Chemical Engineering, University of Technology, Malaysia. So we are taking this example from this work, so we will solve it using UNISIM software. Now UNISIM is one of the process engineering softwares that is very useful. So you can lay hands on UNISIM, Aspen i6, Aspen Plus, Pro 2, and then for process design problems. Okay, so the first thing for you to do here, let's go to the UNISIM environment. You come here, go to new case. By the time you go to new case, you see components, fluid packages, hypotheticals, oil manager, reactions, component map, user properties. So depending on the process you are modeling, that will determine which of these menus that you make use of. Okay, so in this problem we're going to make use of the components, fluid package, and then reactions. But when we are solving oil and gas problems, we will need oil manager and then also hypotheticals to create components that are not in the standard library. Okay, so the components, let's go to our problem and see the components that we will need. So the question says the interest in production of hydrogen from hydrocarbons has grown significantly in the last decade. Efficient production of hydrogen is an enabling technology directly related to the fuel cell energy conversion device. The conversion of fuels to energy can be carried out by the partial oxidation. The partial oxidation method relies on the reaction of the fuel, for example, methane with A, in order to produce carbon oxides and hydrogen. So we have two reactions here. Methane reacting with oxygen to give carbon monoxide and hydrogen, and then at the same time methane reacting with oxygen to give carbon dioxide and hydrogen. Okay, so these two reactions happen together, so this is what is called parallel reactions. Okay, so the two happen at the same time. So we'll need methane gas, we'll need oxygen, but since for this process we'll not be using pure oxygen, which would be expensive, we will be using A. So A would have mixture of oxygen and nitrogen, so we'll need methane, nitrogen, oxygen. That's the A we'll get will contain nitrogen. You know, A is about 78% nitrogen and then 21% oxygen. So we'll just do that. So we'll need methane, oxygen, nitrogen in the A that we are going to use, carbon monoxide, carbon dioxide, and hydrogen. So let's go to UNISIM environment. So at the, what was that error for? Okay. At the UNISIM environment, we will now impute those components. So you come to add, then we'll need methane. You click on methane here and then click on add. Then the next thing we'll need is oxygen. You can type it here, oxygen. what's the spelling again? Oxygen. Okay, you have it there. Then nitrogen, you double click to enter. Carbon monoxide. Okay, so that doesn't seem to work, so we now use the formula CO. We have carbon monoxide, you add, then CO2, you add, okay, then hydrogen. That doesn't seem to work, so we use okay, so simulation name or full name, hydrogen, we add. Okay, so we have that there as a component. So we've listed all the components that you would want. So when you finish listing the components, you close here. Then we go to fluid package, and these are the fluid packages. If you check, you see names. Most of them are funny. Antoine, we see Ben Robinson, and the rest. You know, in the first degree, when you are doing thermodynamics, these are correlations that you use to estimate the process parameters manually. So, and then like in my university, we had to estimate for Penn Robinson, for Robinson Swarf, and then like that, and then we compare the results. So we're going to use Penn Robinson. So you don't get to worry about which fluid package to use. If you use the wrong one, it will not show green here. Okay, so we close that. Then we go to reactions. So you add reaction. Then you see conversion, equilibrium, heterogeneous, catalytic, and the rest. So depending on how rigorous the work you are doing. Now, if it is research that you need to consider the kinetic parameter, the kinetic parameter, activation energy, a pre-exponential factor, and the rest. So you make use of catalytic reaction, and then if the reaction is in equilibrium, forward and backward, to use equilibrium, and then kinetic, simple rates like that. So, but if we just want to, if you have already gotten the conversion, and then we want to like do a kind of a material balance, okay, material balance. So that's when you use conversion reaction. So we just use conversion reaction. You come to add, then you go back to the equations. Okay, the first equation requires methane, oxygen, and then like that. So you come back here, you drop down here components, you pick methane, drop down, pick oxygen, drop down, pick carbon monoxide, you drop down and pick hydrogen. The nitrogen that we are going to have from A, nitrogen is inert, it's not going to appear in the reaction. Okay, so later on, highest we can do is to push it from the system so that it does not accumulate in deleterious quantity. Okay, so you have that. Then we put the reaction stoichiometry. So stoichiometry is the numbers that are written here, like what mathematicians call coefficients with their variables. So this is 1 here, 0.5, 1, and 2. Then for reactant, since the reactant depletes, so we use minus for reactant. since product increases, we use plus for product. So we are going to say -1 minus 0.512. Okay, so let's go there. Methane. Okay, you now see that it has, the software has given you the molar mass for the compounds. So that's the beauty of using the software. It estimates a lot of properties for you. So -1 for methane, minus 0.5 for oxygen, and then 1 for carbon monoxide, 2 for hydrogen. Okay, so by the time you do that, if the equation is balanced, you see balance error here 0. It will zero out. Then that's the stoichiometry. You now come to basis. At basis, you from year 1 chemistry, you might have been taught how to estimate reactant that is limiting reactant and the one that is in excess. So from here now you see that methane here is the limiting reactant, or the reactant that is most expensive. Okay, so we base the reaction parameters on that limiting reactant. So for methane, base component methane, then the conversion will pick 40%. Okay, that might have been result from maybe lab work, and then we saw 40% conversion as being optimum. So for these two reactions, the conversion has to add up to 100. So the first conversion, we take 40% conversion of methane, and then second conversion 60%. Okay, so that's that. So the first reaction has been imputed, then we close that, and then we add another reaction. Since there are 2 reactions, so that one is also going to be conversion. You add, and then you go and check the equation. So -1 minus 1 1 minus 1 minus 1 1 2. Okay, so we go back there, we pick methane, oxygen, where is it, oxygen, this time carbon dioxide, and then hydrogen. So we say -1 minus 1, that is the stoichiometry, and then 1 and then 2. All right, so that balances. We go to basis. Methane is a limiting conversion, this time 60%. So it means the first reaction, you know, these 2 reactions are happening together in the reaction vessel. So the first reaction 40% methane converted, second reaction 60% methane. So you now have this product coming out. Okay, so we close that. So we have our 2 reactions. So the next thing we are going to do is to add reaction set. So you click on add reaction set, and then you come and add reaction 1 and then reaction 2. So we add those 2 reactions, and then we want to determine the, excuse me, let me check something from here. So that is done there. Okay, and then let's view it and see. Okay, so we want to rank the reaction. What order should the reaction occur? should reaction 1 and reaction 2 occur simultaneously, or should one occur first? So we come to ranking, and then we activate it. If we want, you can just put here 1, 2, or 0, 1 if you want them not to occur at the same time. So I put 0, 1. That means reaction 1 should occur first before reaction 2. Okay, we accept that, and then I think we've added reaction set. Is there any other thing to be done here? Reaction set, you can choose, you can change the name, and then maybe you call it oxidation reaction. So these has combined the two reactions that are happening in the system. So we close that. So having closed that, you now add it to the fluid package. Add what you have done to fluid package, so that by the time you enter simulation environment, you can see it to make use of. You say add to fluid package, add reaction set. Then I think we are done. You go to enter simulation environment. So this is the environment that you do your connection. I was tempted to say wiring. Okay, you do your connection, and then that's, you connect all your equipment. If it's a full plant, you line up your pumps, your heat exchange, your separator, your mixers, and then everything that you would think of, you find them here. Okay, the stream. Now let's see, we come and pick material stream. We want to see the materials. We want to fit in those two reactants. Okay, so we put this in. So we open this materials. We want to specify it, and that will be for this first part of the reaction. So we want to specify that. So we now say, so for the material, we're going to put methane. We need two material stream. Like assuming you have in the plant, in the process plant, you have I wanted to say you have two tanks. You may not necessarily store the gases. Since it's gases, you may not necessarily store them in tanks. So what you do is that you receive them from maybe the gas company. Okay, so they send it through pipeline to the gas company. So you now connect the gas manifold to your reactor. So what we are now looking at is the connection, the first connection, the first gas manifold will now be methane. Okay, so that's what we are specifying here. You know, methane is natural gas that you got from gas company. It comes as a result of drilling for crude oil. If it's associated gas, it comes with the crude oil. If it's not associated, it comes from a pure gas wells. So you now get this methane gas from the company, or maybe methane biogas. Okay, so we call that stream methane that will be coming in. Okay, so we specify the temperature that the gas will be coming in. We can take standard temperature, or maybe something around the ambient temperature of our environment. Okay, like here in Nigeria, our ambient temperature is around 30, but for the sake of standard, we just use 25 so that the work can be reproducible. Then the pressure, we take 2 bar. We take 2 bar. You know, pressure is as this is coming from the well, the pressure that the pump the compressor is sending it down. Okay, so it has converted it to kilopascal. So you have the reading here. So you have 200 kilopascal. So that 2 bar that we imputed, the equivalent pressure reading is a 200 kilopascal and then 29.01 psia, pounds per square inch absolute. What is this information for? Change color scheme. Let's ignore that. Okay, so then the flow rate, we take a base, we just take 100. You know why we take this is like this flow rate, you can always change it. You can always change it to see how your system behaves. Okay, so that is the stream that will have methane. Let's go back and see. So we're going to have methane and oxygen. So it's just like maybe the welders welding, they will have acetylene bottle and oxygen bottle. Okay, so or you are cooking, you have propane bottle and oxygen coming from the environment. So methane, so we specify methane now. So we have put in this, so the degree of freedom here for the conditions is 3. So if you specify any 3 condition, you are good. Then you go to composition. Composition for that stream we would assume that is 100% methane, and then actually it's 100% methane. So everything is working and well. That's why you have green here. Okay, so that means that stream has been fully specified. So 3 properties here, and then 1 for composition, making it 4 degree of freedom to specify your material stream. Okay, so we go for another material and then we put it here. So what we are looking at now is that by the time you have the natural gas stream, the methane, you need oxygen. So the oxygen might likely come from a compressor. Okay, a compressor, and then let's specify that it will come, and we still take 25 degrees Celsius, and then 2 bar, and then the flow rate we use like 260. Okay, so the reason for that is we need oxygen in excess for the combustion to be complete, for the reaction. You know, that reaction is a typical combustion process, so we need a good amount of oxygen, and mind you, is coming with nitrogen and nitrogen. Okay, so we come to composition. At the composition, that stream would contain nitrogen. So approximately in engineering, we approximate the value of A to be 79% nitrogen. So that will be a mole fraction of 0.79. Then for oxygen in the A, that will now be oxygen 21%, and that should balance up to 100. Okay, so in terms of mole fraction, that's what you have. So that is solved. So we have the 2 streams, except that we didn't change the name here. So we come here and change the name and put here A. Okay, so that stream is A. Alright, so we close that, and then we come and get our reactor. So we want to feed these 2 streams, these 2 reactants into the reactor and see the product that will come out. The essence of this is to see the product that will come out, and then the composition of the product. So it's a starting point in process design, what we call the front end engineering design. So the values you get will help in the detailed engineering design. So it is the starting point of every design process. So we come to general reactors. We see different types of reactors here. So we come directly to convection reactor. We drag it down. Okay, I thought it will not follow me. You keep it here, and then we want to wire it. You connect the pipe down. Okay, so you double click to do that. So here we have connection, and then the inlet, A will come in, and then methane will come in no particular order, and then the outlet, we will just call this top product, and then this one bottom. Okay, bottom product. So we are done with wiring. Other parameters. Energy is optional. Energy is optional. That one comes to play if you want to look at heating the reactor or cooling the reactor. Okay, so we come to reaction. So when you come to reaction, you come to reaction set, and then that, you see why we said you create reaction set and then put it into a fluid package. So all that we did during specifying of this thing is here now, so you now accept it. So everything is good. That's why it's giving you okay. All right, so we have specified the reactor fully, so everything is looking fine now. So now let's see, in our feed we had methane coming in at this process condition. When we say process engineering, we are primarily a process engineer or a chemical engineer. Our work is primarily to specify process conditions. Okay, so we specify the temperature, the pressure, the flow rate, and other parameters that will be useful to the process. Then from there we do other modeling, and then so that the guys that will be doing the instrumentation, the control, the mechanical design, and then they would make use of the parameters that we feed them with. Okay, so methane comes in with these process parameters, and then this is the composition of the methane. 100% methane. We close that. A came in, the conditions here, and the composition. So we want to see at the exit, the top of the reactor, what comes out. So at the top of the reactor we have 101 vapor fraction to be 1. That means the product going out there is 100% vapor. Okay, it's 100% vapor, and it's living at a temperature of 844 degrees Celsius. Something that started with 25 degrees Celsius is now ending with 844.7 degrees Celsius. So that should send a signal. This temperature, would the system withstand it? This temperature, what type of material should be used in the design? We feed the mechanical engineers with that. Okay, what type of material would be used for the design to withstand the this high temperature? Okay, is it a process that the temperature would melt the material? So we have that there, and the pressure is still at 2 bar. Okay, fine. Now there are some processes that the pressure will get so high. Okay, so we now look, would our process withstand the pressure? Okay, so with that we see, and then the flow rate now increases to 454.6 kilomole per hour. So that's the flow rate. It started with 100 and then 260, and then this is what you have at the top. And then let's see the composition that comes out there. The what comes out from that top is now 5.5% methane, no oxygen. Oxygen has been completely used up. Nitrogen comes out, carbon dioxide, and the rest. And then these are the percentages. So the hydrogen is produced at about 32.8%. mole fraction. So those are the results there from the top. Let's check the bottom if there's anything there. Now the bottom, if you check the bottom, the flow rate at the bottom is 0. That means all the products are coming out from the top. Okay, so that's how we use UNISIM to solve a reactor problem, a very simple reactor problem. Now, Adibin, if you try solving this problem manually, you will appreciate why we use UNISIM for it. Alright, so thank you so much, and then do the needful, subscribe, share, like, comment. I'll be glad to hear feedback from you. Alright, thank you very much, and bye.